Let's take a look at this question over here. An electron has a de Broglie wavelength of 2.80 times 10 to the power negative 10 meter. And they ask you to determine the magnitude of its momentum and its kinetic energy. So from wavelength, you need to determine the momentum and the kinetic energy. So for chapter 8, right, there's a lot of variables involved. You talk about accelerating voltage, you talk about kinetic energy, you talk about momentum, wavelength, speed. There's many quantities that we're talking about. So it's good if we are able to relate between all these quantities here in a single map. So this is what I'm going to introduce to you, a map to show how everything relates to each other. So for matter can be things ranging from electrons or protons to other ions maybe, okay? When we're talking about chapter 8, usually the matters are these kind of particles. Okay, so we need to be able to relate between different quantities starting from the accelerating voltage. Why do we start from the accelerating voltage? You can refer to a derivation video, because it is the accelerating voltage that we are able to manipulate actually. Then once we manipulate the accelerating voltage, we are able to cause changes to the kinetic energy. Okay, so in this case, to make sense of it, the greater the accelerating voltage, that means by you're pushing the electron harder. So if you're pushing the electron harder, that means it accelerates more. So it will end up with a greater speed. So greater speed means greater kinetic energy. So that's how we relate between kinetic energy and accelerating voltage. Then from there onwards, we can relate kinetic energy to momentum. So momentum, the symbol will be P. Okay, the idea is still the same. Greater kinetic energy means by it's moving faster. So P is equal to mv, so your momentum should also be greater as well. So they are positively correlated to each other. Then from momentum, we can move on to discuss two things. You can either discuss about speed. So momentum related to speed is quite direct, just P is equals mv, or you can relate it to wavelength as well. So wavelength will be lambda. Okay, so this is basically how you need to know how everything connects to each other, and we need to know the equation that connects them. Okay, the equation that connects them, all of them can be obtained from the derivation video. So here I'm just providing a summary only. So to relate between the kinetic energy and accelerating voltage, you can see K is equals to EV. Okay, but this equation, because you're substituting elementary charge, right? This equation is only valid if your matter is an electron or proton. Okay, if it's other kind of ions, let's say if it's magnesium 2+, or it's alpha particle, or if aluminium 3+, all those kind of particles, you have to be very clear whether there's more protons or electrons, or there's more electrons and protons, by how much, and from there you can determine the charge. Okay, it is a charge that you need to put inside here, but for most of our cases, for most of our questions, it's electrons that we're talking about, or in some cases there are protons. So in this case, using using elementary charge 1.60 times 10 to the power negative 19 to put here, it's still okay for most of the cases. You only need to be very alert unless when they talk about particles that are not electrons or protons. Okay, so kinetic energy and momentum, to relate between them, you have an equation K is equals to P squared over 2m. This equation is actually quite widely used when we enter the field of physics in university. It is used in relativity, it is used in mass energy equivalence, it is used in nuclear particle physics, quantum physics. They are all quite widely used. But I think this is your first exposure to this equation in a matriculation level. So don't worry too much, just an exposure, but it will get very significant when you enter university to study modern physics in the future. Okay, so K is equal to P squared over 2m. Momentum and speed, this equation you have learned it since Form 4, I think, or Form 1. Okay, P is equal to mv. So for momentum and wavelength, it's P is equal to h over lambda, the equation that is related to de Broglie's hypothesis being proven over here, where you can relate between the particle properties of matter and also the wave properties of matter in a single equation. Okay, so this is how we relate everything when we talk about matter. But occasionally they are not interested about matter, occasionally they are interested about light. So for light, or for photon, okay, or any kind of wave, EM wave, okay, we are not able to discuss them just like exactly like matter. Okay, light is different from matter, so the discussion over here to relate everything, it uses a different idea compared to what we see in this map above. Okay, for light, most of the time we are relating between kinetic energy but honestly, if we don't talk about kinetic energy over here, why not? Because we are talking about light. Light is massless, right? So light is massless, technically it is inappropriate to call this as kinetic energy, because kinetic energy, you know, half mv squared, right? There's a mass needed for you to have kinetic energy. So in this case, we are not talking about kinetic energy, we are talking about energy actually. Okay, so for light, we are focusing on energy, and you need to know how to relate it directly to wavelength. Okay, most of the time you only need to directly relate to wavelength. So in this case, we know that the equation will be E is equals to hc over lambda. Okay, so this is the only equation that is important when we discuss light, but for matter, you need to know how everything connects to each other. Okay, so that's matter and light. And the last thing I want to add on before I proceed to solve any question is, you have to be clear with the unit conversion of energy. Okay, energy, if we talk about the SI unit, then energy is in the unit of joule. But in particle physics or in nuclear physics or in any kind of small scale kind of physics, particle, quantum or nuclear kind of physics, energy is usually expressed in the unit of electron volt. Okay, whereas 1 electron volt is actually equals to 1.60 times 10 to the power negative 19 joule. Okay, so this 1 eV here, you can think of it as the energy, the change in energy okay, experienced by an elementary charge. So it's either a proton or it's an electron, it's up to you. But when an elementary charge moves through a potential difference of 1 volt, if you have one single elementary charge, let's say an electron, move through a 1 volt potential difference, you'll be able to gain or lose by this amount of energy. How do you do it? Well, you can see that the change in energy is equal to Q delta V. Okay, this is just concept. This is not, it's just for you to know why 1 eV is equals to 1.60 times 10 to the power negative 19 joule. Okay, so the change in energy experienced by an elementary charge, so this Q here can be substituted with elementary charge, and the potential difference over here is 1 volt. So if you want to know how much is the change in energy, this is E, this is 1 volt, so therefore you are able to get 1 eV. Okay, so the change in energy is equivalent to 1 eV. So 1 eV is how much? If you choose to substitute, you can say 1 E is 1.6 times 10 to the power negative 19 joule, coulomb, sorry, this is E, 1 volt. So you get the answer is equals to 1.60 times 10 to the power negative 19 joule. So this is how you get the relation between 1 eV and 1.60 times 10 to the power negative 19 joule. So you need to be able to switch flexibly between these two units, but every time when we are substituting values like wavelength, momentum, everything is in SI unit, right? Then the energy that you calculate is in the unit of joule, but you need to convert it in EV because answers are usually expressed in EV. Okay, so you have to be able to convert between these two units effectively. Okay, so let's try to solve the question. Question A first. Question A asks for the momentum and you're given the wavelength. So you need to relate between momentum and wavelength. So this is the equation that you pick. So P is equals to H over lambda. So now it's just substitution. H is a Planck constant, so it's 6.63 times 10 to the power negative 34. And wavelength over here will be the wavelength given. So this is 2.80 times 10 to the power of 10, negative 10. So from here you can get your momentum to be equals to 2.37 times 10 to the power of negative 24. And the unit for momentum is mass times velocity, right? So it's kg ms negative 1. So kg ms negative 1. Okay, next, they ask for the kinetic energy, both in joule and in electron volt. So if they're asking for kinetic energy and you relate it to the wavelength given, So you need to go through from kinetic energy to momentum to wavelength. So you need to combine these two equations in order to get the equation that relates between kinetic energy and wavelength. So K start with is equals to P squared over 2m. But since our P over here, momentum, is related to wavelength by this equation, we are going to substitute it in to get h over lambda square over 2m. So now it's just manipulation. You can get h squared divided by 2m lambda square. You can calculate everything right now. Your Planck constant is 6.63 times 10 to the power negative 34 square divided by 2. M here is a mass. So what is the mass that is moving through the potential difference? It is the electron that is moving through potential difference. So this one will be 1.6, mass of electron, not charge of electron. Mass of electron will thus be 9.11 times 10 to the power negative 31. Okay, sometimes there's 2 decimal places for this mass, sometimes there's 3 decimal places for this mass. So just be careful, refer to your constant sheet to get the exact value. For lambda over here, we have the lambda being given to us. So we're going to substitute it in 2.80 times 10 to the power negative 10. Then you need to square it because that's the equation. The square for both the Planck constant and the wavelength. So if you calculate everything, put inside your calculator, you get an answer of 3.08 times 10 to the power of negative 18 joule, which you can continue to convert it to EV because that's what they want. So 3.08 times 10 to the power negative 18 EV. 3.08 times 10 to the power negative 18 joules, you want to convert it to EV. So you would like to eliminate the joule, you like to introduce EV. So we know that 1 EV is 1.60 times 10 to the power negative 19 joule. So the result of the calculation is you should have an energy of 19.23 electron volt. Okay, if it has a wavelength of 2.80 times 10 to the power negative 10. Okay, so this problem here, Jenny, I'm just introducing you how to relate between different parameters of the electron or for the electron wave. What are the different parameters and how do you relate them together? And we apply this relation here in these 2 questions to understand how to apply it, to understand how everything works here. Okay, so that's it for this question. Thank you very much.